So it should be clear that in order for Monte Carlo simulations to give useful results, one needs an abundant supply of random numbers and specifically IID uniforms, standard uniforms taking values between 0 and 1. So where does one obtain such a supply of random numbers? So the true random number generators are outputs of some physical process or some device, and in some cases these outputs may need to be processed and filtered and then used. These sources could be noise, these sources could be radioactive decay. For example, we did discuss Martian processes briefly in our past lecture, and there is a very strong theoretical basis to suggest that the inter-arrival times between these decay events are IID exponential random variables. So if we could record these time instances, we would have a sample of IID exponentials, which then we can convert to IID uniforms, which we will learn about these transformations later in this lecture and the next. So we could use them for the purpose of Monte Carlo simulations. And in many cases, the quality of these true random numbers are very good. They pass all important or all relevant tests of randomness. In fact, these tests we are going to look later in this lecture. The problem is that a true random sequence can be stored for future use, but it cannot be recreated. And for our purpose in engineering, we would need to be able to reproduce a random sequence for verifications or for use by a peer or a colleague, which is different from the needs of cryptography, for example, where you would not like this sequence to be recreated easily. It's also, in most cases, true random numbers are slow and more expensive to generate compared to computer-based pseudo-random number generators, but there are notable exceptions. Just earlier this year, there was this paper in Science where the authors discussed very fast generation of true random numbers of the order of 250 terabits per second using the chip scale laser that they describe. So we should mention such advances. But for now, it is the computer-based pseudo-random number generators that are almost exclusively used for science and engineering applications. So what are these pseudo-random number generators? These are sequences of numbers that are generated by a very precise, deterministic, reproducible algorithm, and fast, very fast. But even if they are completely deterministic, they have all the appearance, all the required appearance for the application at hand of being a truly random sequence. So that's very important. Now we would like such pseudo-random number generators to have a set of desirable properties, especially the ones that have highlighted in bold. Accuracy, which means they must be IID uniforms. They must have a very long period. Period means the sequence length after which it starts to repeat itself. So all the IID characteristic is lost. And machine independence, because we would like to test someone else's algorithm or someone else's results, or have someone else test our results. So the same sequence must be created regardless of the particular operating system or particular machine at hand. Now, pseudo-randoms are most commonly generated with the help of the multiple recursive generators, which uses modular arithmetic, m being the modulus, and with each successive output of xi, it's normalized by m, which produces the standard uniform deviate. K is the order of the generator, and the maximum possible period of the generator depends on m and k. Now, when k is equal to 1, we have the classical linear congruential generator, which we are going to look at in the next slide in some detail. But this idea of multiple recursive generator, it can be taken to an RNG based on recurrence modulo 2, which means directly in terms of bit strings and sequences. So the operations are like this. The first set is the twisting type operation. The second step is the tempering type operation, and the third set of equation that you see, it's basically the output of the random number generator, the standard uniform, written out in terms of the y's, which depends on the word size. One of the most popular generators in this class is the Marsenne twister algorithm, which has very good properties. In fact, the default generator in MATLAB, which is what we are going to use in this course, is the MT19937 algorithm, which has a huge period, 2 to the power 19937 minus 1, which is something like Google to the power of 60, so it's practically infinite. So the issue of long period is solved. If you would like to read further, I have listed 2 references here. In the next 2 slides, we are going to look at the linear congruential generator and some examples of pseudo-random number generators.